most packets, in fact, the vast majority of packets in Skype, under 200 bytes. So once again, you see a very nice clustering of packets, versus other protocols. And once again, Skype is just being used as an example. We actually have some other examples with other protocols later showing, that all protocols tend to cluster in a certain way. And then finally, now we have the average inter-packet delay. And this is the amount of time between two subsequent packets in one direction, specifically from the client. And this is once again going to be one of those things where streaming protocols like VoIP or video are going to have a very, very small inter-packet delay because they want to make sure the next frame of video gets there. They want to make sure the next word in the sentence gets there. Whereas it doesn't really matter so much. If your web page is delayed by, 2/3 of a second, nobody's really going to complain. But if you all of a sudden have voice traffic dropping or video frames dropping or audio frames dropping, then you have a real problem. So once again, a lot of protocols can't help but run this way. They have to have a very small inter-packet delay. And other things have to have very large inter-packet delays. If you're doing something like, say, XML-RPC, that takes a very large amount of server-side processing because, you have to parse the XML, you have to do all this, you have to do all that. And so it's going to be slightly slower than, say, a regular HTTP request or something like that. So you can cluster that as well. And if we can go to the graph, you can see once again that Skype, very, very, very banded. We have those packets up at the top there. Those were actually the initial setup packets, and those were sort of, they took a little time to get there. But then almost all of the packets band into a very, very consistent amount of time. And that is very important. That's not just that they're small, it's that they're consistently small, that they're in the same sort of area. You don't want to have one packet come very quickly and then one packet come very, very slowly and then one packet come in the medium, in the middle. You want to have it as the machine is ready to receive the next packet is there. So you need to have predictability. And that's something that, once again, it can't be avoided. If you're doing a streaming protocol, you have to have something that bands like that. So if we can go to the next slide here. And then this is the same coordinate, but in the alternate direction. And once again, everything I said for that, everything I said for that applies here as well. You can't have just arbitrary times in very many protocols. Whereas some protocols, you might have intentionally unusual timing. That's something that's trying to avoid detection. And once again, that's going to look completely random and is going to differentiate it from another protocol. And that's also very, very important. And then this is the graph. And as you can see in the other direction, this is without the packet. We don't see the session setup here. And so all of the packets band very, very well because they're flying very, very quickly and very, very consistently for voice traffic. And then this is traffic difference. And this one takes a little bit of explaining. So aren't you glad that you have me here? Traffic difference is basically what the ratio is between the two parties. Is one party sending significantly more traffic than the other party? Are they roughly the same? Things like that. And once again, if you have massive amounts of traffic in one direction, you're probably looking at a client-server relationship. Whereas if you have a bunch of packets in both directions and the ratio is roughly 1-to-1 or somewhere very close to that, you're definitely doing some sort of bilateral communication. And so once again, that's something that's very useful to identify a protocol. You're not going to see, for example, encrypted HTTP having a lot of traffic in both directions. You're going to see very large amounts of traffic in one direction and very small amounts of traffic in the other. And so if we can go there. So as you can see, Skype, sorry, because you're tight. Skype is, this is hard to see in two dimensions, but that's actually relatively linear because you've got one side talking, and then one side, and then they stop talking for a while, and they talk, and they stop and they talk, and you get this very nice linear progression over time of the difference between the two parties in traffic. And that would actually be easier to see in a 10-dimensional graph, but unlike Rohit, I only see in 3 dimensions. So, and now we have the variances. And these are all treated as separate coordinates. And these are the standard deviations for all of the coordinates. So like you have the standard deviation of the packet size to client, the standard deviation of the packet size to server, the standard deviation for inter-packet delay, both client and server. And that way we can see if things tend to be very, very random or if they tend to fall in a fairly normal distribution. And that's something that is, once again, very useful to identify a protocol. If you have a bunch of packets that fall in a very narrow range and don't tend to fall out of that range, you can assume certain characteristics about that protocol. So if we want to go there. And this is Rohit's favorite coordinate, so I'm going to let him talk about it. So I'm going to hand it back over to him.
So the Shannon entropy is used in the information theory for trying to figure out how random a data is. And the same concept is actually also used for figuring out how to compress data. And the way you define this entropy, the mathematical expression is if you have a series of outcomes, if you have an experiment and there are outcomes x1 to xn with probability p of xi, what you do for finding the Shannon entropy is take the product of each probability with its log to the base 2 and sum over all your data set. For our case, what we are doing here is when we see these protocols and the packets, we try to take a dynamic probability of what characters are occurring in the packets. So what we do is once we have seen 3 or 4 or 5 packets, we will compute a histogram of the character and its frequency. And that particular histogram we use for computation of the Shannon entropy for that protocol. And to get an intuitive feel of what this number is, let's assume that you have a protocol which is just sending a bunch of A's in all the packets. So for such a protocol, your probability of character A is 1 because that's the only character occurring in that protocol. And therefore, if you take log of 1, which is 0, your Shannon entropy comes out to be 0. And again, that is intuitive because this protocol is not sending any random data. And if you were to compress this particular protocol, all you could say is how many times the number of A's are happening in the packet. So I don't need to send, like let's say the protocol is sending 5 packets, each 1500 bytes worth of A's. To the other end, if I want to compress and send the same information, I can just send a character 7500, a number 7500, and because the protocol is not random. And that's why it allows for an easy compression. Similarly, let's say if you had another protocol where character A and character B occurs equally likely, each of the probability is half, and once you compute the Shannon entropy for that, you get a number of 1, which tells you saying there is some randomness, but it's really not totally random. And what is the maximum entropy you can get from the character set which we are using is if you have letters from or characters from hex 00 through hex FF, and they are all equally likely in a protocol, implying the protocol is totally random because any character from null to hex FF is occurring with equal probability, you get the max Shannon entropy, which is probability for each letter is 1 over 256. And once you take 1 over 256, log of 1 over 256 times the whole thing 256, the answer is 8. I mean, you can do the math. But in our case, therefore, the entropy is bounded between the values 0 and 8 for any protocol which we have seen. And if you see for Skype, right from the beginning, on the y-axis is a scaled entropy, which I'll talk about later, and on the x-axis is the number of packets. You see the entropy for Skype is at its maximum right from packet number 200, implying that it's using very random data or encrypted data, which is the characteristic of that. So for training purposes, we had collected a lot of data. And since we were actually initially focusing on Skype as an example, we tried to collect a lot of data for Skype. There's another voice or IP application called Gizmo, not as popular as Skype, and a lot of UDP traffic like DNS, NTP, NetBIOS from both the corporate and some of the university environments. And we tried to make sure that there was enough variation in the samples we were collecting. So we made Skype calls within the same office. We made Skype calls within the same city. We come from Austin, so we made calls in Austin. We made calls within the United States, and we also made international calls from to India, where I come from. And that gives us a good amount of deviation in the data. So that makes our data set very rich. Just one thing to kind of keep in mind with the data set is we didn't go and explore things like dial-up links. So all the inter-packet delays which we were experiencing are all typically on broadband or LAN environments. So that factor of dial-up environment is not taken into account for this data set. The other problem we faced is, if you look at all the coordinates, some of them are measuring packet sizes and some of them are measuring times. And both of these things are on a totally different scale. Typically your packets, the maximum you can have on the LAN is 1500 bytes. I mean, you can have jumbo Ethernet frames for 9000 bytes or so, but in our case we didn't have any of those. And on the other hand, the inter-packet delays, they are all in milliseconds, or fractions of milliseconds. So what we had to do was, to be able to make sense of the data while plotting it in this 10-dimensional hypercube, we had to scale the coordinates. So everything was scaled to a maximum, and we took the maximum as 2000. So all the entropy was scaled to 2000, as well as all the inter-packet delay, they were all scaled to a scale of 2000. And that's what you see on all those graphs where the max was around 2000. The other interesting thing which you already saw from the Skype graphs is, if you let 200, 400 or 600 packets pass by, the statistics quite stabilize. So all the coordinates what we are seeing, either they try to get to a single value asymptotically, or they fall in distinct bands. And all the other traffic also has the same characteristic, where either they asymptotically stabilize to a standard value, or they have very little variation in the set of values.
And now it's back to me. I'm sure you all missed me very much. So as Rohit said, we did scale all of the coordinates, but that's not all we did. And what we're going to talk about now is that, we've got all this data, we've got this massive data, and we've statistically analyzed it, and we've massaged it and everything, but now what do we do when we want to identify a completely random stream, one we've never seen before? We want to compare it to that huge dictionary or database of pre-trained data. And so the way the data format works is you have, for every packet, say for packet 0, packet 1, packet 2, packet 3, you have a list of packets, and this is per protocol, a list of packets with the statistical information for each training set. So you have this massive data set where the first packet of this protocol in this stream is this, the first packet of this protocol in the other stream that we train with is this, and so on and so forth. And then we do that for every one. And the statistics are calculated for every packet. And the reason, the statistics are calculated for the entire stream up to that packet. We do some clever tricks to avoid having to recalculate things, but when you look at, say, offset 4, you're talking about the entire stream, how it looks as of packet 4. And we do that because we want to make sure, we don't want to say, see the first SYN and the first ACK and say, oh, that's Skype, of course, Skype does SYN ACK. So that obviously doesn't work. It also is no good, really, because it doesn't do SYN ACK. But anyway, so once we get all this in this big cube and we do everything, then we have two distance metrics that we use. The first one is the normalized or scaled Euclidean distance. And that's your standard high school geometry Euclidean distance, except that it's extended into 2 dimensions instead of 3. And it's also scaled and then averaged. So we take a point, we define a point for the unknown protocol in that space, and then we take its distance to every other point in the protocol we're testing against, and we do this for every protocol we're testing against that we know about. And then we take the averages of the average of all those distances, and we say, okay, what has the lowest distance? And that's the lowest distance. And we hold that, and then, if we can go, next slide, please. Then we go and we take the Mahalanobis distance. And this was one of those things that is just all sorts of fun, and great fun to code. And the Mahalanobis distance